Hello, everyone, and welcome to Science Explosion. My name is Zach, and this is Hudson Public Library. All right, so today we're going to be talking about surface tension. All right, so what does that mean? So I always think it's a good idea if you don't know what a phrase means to try to break it down. So surface, I'm sure you know what it means. Like this is the surface of this thing here. This is the surface of my water. It is pretty self-explanatory on that one. So tension is the thing that kind of either pulls it apart or holds it together. So when you put those two things together, it is the tension of the surface. So it's the things that pull apart and hold together of the surface. All right, so if that doesn't make sense, don't worry. We're going to be doing a quick and easy experiment to show you how that works. All right, so this is going to be a simple experiment. All you need is a coin. I'm using a nice shiny new 2020 penny. And then the other thing you'll need is some water. And you'll need a way to drop it drop by drop. So if you have a little eyeglass dropper or food coloring container. So this was an almost empty blue food coloring container, and I refilled the rest of it with water. And I think that'll really help too, because you should be able to see it just a little bit better on the screen here. So that's all you need is some water and a coin. All right, and you do want to make sure that your coin is in fairly good condition. If there's a large chip in the side, it won't work. And you'll see why. All right, so we're talking about surface tension, which just means how well surface of something is holding together. Now, you might remember, I mentioned this on the capillary action video, which was the walking water. And so if you know that, you might know a little bit about how water tends to stick together. And if you haven't seen that one, I would urge you to watch that, of course, but also just a little quick reminder. You can see if you look at any water bottle, you notice that the water curves up when it gets to the edges. That's because it tends to stick to itself, but it can also stick to other things. All right, but today we're talking about how water sticks to itself. All right, so you're going to get your coin laid flat. There's a tiny little bit of a curve on here, but that's flat enough that we should be able to get this. And then you're going to take your dropper. Now, before we do anything, in science, it's always important to make your hypothesis. And so what you're going to make your hypothesis on this time is how many drops of water do you think you'll be able to put on to the head of your penny or whatever coin you're using. So what do you think? Do you have a number? Or you can pick a range if you don't know exactly how much it is. So I've got my guess, but I'm not going to tell you what it is because I have a little bit of an idea of what it's going to be like. And I don't want to ruin what your guess might be. So think of how many it will be to fit on there. And then we'll just get started. We'll see how long this is. So you can count along with me. 1, 2, and you can see how large they are already. 3, 4, 5, 6, 7. I don't have the steadiest hands in the world. 8, 9, 10. Ooh, look at that. So I want you to take a look at it. We're at 10 so far. What do you notice about this water? So if you're doing this yourself, you can really see it. What would you expect the water to do when it gets on the surface of the penny versus what's actually happening to it? All right, we're at 10, 11. Ooh, look at that. That's looking pretty full. So what do you notice? So we're at 11 so far. So what I'm noticing here is that if water didn't stick to each other, it would just be a tiny little pool until it got to the edges, and it would spread out over the penny. But what we're actually seeing is it lumps together in a big clump, and then it's tall. It's about as tall as this penny is, maybe actually even a little bit taller. So it's sticking to each other instead of rolling off the sides like you would really think it would. All right. 12. Oh, look at that. It's still there. 13. Look at that. It's still not spilling off. 14. All right. So now you can see that even though it's not spilling over the edges, it's actually farther out to the sides than the penny is, and it's still holding together. 15. How many did you think it would have? Did you think it'd be this many? 16. All right, so now it is visibly over the sides, but it still hasn't spilled. 17. It's starting to almost look like it's enveloping the penny, which means taking over it. 18. 19. 20. All right, so you remember how it looked like it couldn't hold any more. Oh, look at that. I bumped it and that made it spill over. I think I probably could have gotten maybe a couple more on there. But we got it to 20 until I bumped the table. And it was able to be double what it looked like when it was 10. And when it was 10, it looked to me like it was completely full. It was about to spill over. But we were able to get 20 whole drops onto this. And keep in mind, if you have a smaller dropper, your drops are going to be smaller than this, and you'll be able to fit more on them. But these are fairly large ones. So this looked like if water didn't stick together like it does, it would completely spill over way before we got 20 drops on here. So I got 20 drops on there before it spilled over to the side. So I think that is really great. All right, so you might be wondering, okay, so water sticks together, and keep in mind this is going to be liquids in general, not just water. But you might be thinking, okay, Zach, that might be somewhat interesting, but why does it matter? Well, this is something that is really important when you think about scale of things. So if we were to do this in a large thing, so this can hang off like double the height of the penny and hang off probably, I think I might have gotten maybe a centimeter off to the side, so that's quite a bit. If we were to do this the size of a swimming pool, it wouldn't be able to be the water double over the side of the pool. But you could definitely try this with a full-size swimming pool, and I think you'll notice that you will be able to get it over the lip. Not nearly as much, but a little bit. All right, so this is something that you can actually see outside if you go into nature. So the best time to see this is actually, I think, at least the most interesting, is going to be during the summer. So if you go out to the creek or any other body of water, take a look at the surface. And I want you to take a look at some of the bugs that are on there. So there's a lot of bugs like water striders or anything. Don't look at the ones that are under the water, and don't look at the ones that are flying over the water. Look at the ones that are actually on top of the water. And what do you notice about them? So I want you to think, if you can think about what you've seen there, if you know what a water strider is, that one's absolutely perfect to think about this. So think about how a boat works when you put it in the water. A boat works by floating. So you've got a boat that sits in a thing of water, and it floats because it's less dense than the water. So basically, it's lighter by volume is the simple way of talking about density. But that's how a boat works. It floats. That's actually not what those bugs are doing. So you might think that they're floating on the water, but they're not. It's something way, way cooler than that. They are walking on the water. So they really are. So if you go and lay in the water, you're going to float on the water. because you're less dense than the water. That's why you have to use effort to swim down under the water. But these bugs are actually light enough that they don't break the surface tension. So the surface tension is what's keeping this water together. And you'll also even notice, even though it's spilled over the side, it's still in a blob right here. It hasn't spread out over this whole thing. So those bugs are light enough that they don't break that surface tension. So that means they don't break the tension of the surface. They're not breaking through the surface like you or I would if we were to go swimming. So they're not swimming, they're not floating, they're standing on top of that water. They're light enough and they're spread out enough that they're able to do that. That's actually why you'll notice there are a lot of plants that you see growing on the water, like lily pads. Now, large ones are just going to be floating, but a lot of those are so wide and thin that they're actually not breaking the surface tension of the water at all. They're sitting on the water. All right, so how does this affect you? So I want you to think, have you ever gone on a diving board or jumped into a pool and done a belly flop? All right, so if you have, you know exactly what I'm talking about. And if you haven't, you probably still have somewhat of a good idea. So when you do a belly flop, how does it feel? So it hurts a little bit. So you might be wondering, if water is this thing that I can move through, I can swim through water easily, it pushes out of the way whenever I try to go through it. Well, even though water is liquid and it flows, so it'll go wherever I turn this container. That's what makes it a liquid, by the way, is that it doesn't have a solid shape and it flows, but it will stay in this container. All right, where was I going with that? All right, so thinking about water, it flows like that, but it's still something with mass. So when you push through water, you'll notice that you feel resistance. So there's something pushing back on you. That's why you're able to swim through water. If there was no resistance, then it would be just like waving your arms through space. Waving your arms, if you're out in the middle of space and trying to swim in it, isn't going to do anything. By the way, this is out in space, not in the ship. In the ship, there's going to be oxygen and other types of gases. But out in space, there are no gases for you to put, or liquids or solids for you to push against. So doing this in space, you're not going to move. So the only reason that you move forward in the water when you swim like that is because there's substance there you're pushing against. By the way, you might notice that astronauts are able to do that, and that's because that's when they're inside the ship. They're pushing against oxygen. So normally we don't think about being able to push against oxygen or air in general. And that's because of the way we are on Earth. We're fighting against gravity. It's pretty much something that we can usually ignore. But you can definitely feel that it is something that'll give you resistance too. Just go like this and notice that you feel the wind against your hand. So you can definitely tell that it's there. All right, so think back to doing a belly flop on the water. So I talked a little bit about how swimming through the water works. So you'll notice that even though it makes sense that there's a resistance of the water when you push against it, it might not make sense to you unless you know about surface tension, why doing a belly flop hurts. Because when you go into water normally, the water moves out of your way and you go into it. But when you do a belly flop, it's a little bit different. You're hitting the water fast enough that the surface tension doesn't have time to break. So because you're spread out over a big area, your whole front surface is hitting the water at the same time. And so in that little tiny bit of time, it's like you're hitting a solid. It's like you're hitting the hard ground until just a fraction of a second later, it starts to react like a liquid again. That's surface tension at work, and it wouldn't work otherwise. So that's actually why if you do a dive into the water, you're not going to hurt yourself as long as you're doing the dive right, because you're breaking the surface tension of the water. So I know this is a really simple experiment, and this is really easy to do. So I would really encourage everyone to follow along with this one. I think you'll easily be able to do this. But I think it really shows you something really cool about how water works. And I think when you start to understand the way water works, and it's something that's all around us, you start to notice a lot of really cool things. Water has a mass and it can do stuff and move stuff. So if you notice the creek in town here, I think that's another good example. So creeks all start out with just being little trickles of water. But if you'll notice how deep that creek is, that's because over time, that water is flowing through there and it's carving it out. The Grand Canyon, if you've ever seen that, is made the same way over a very long period of time. It's just water rushing and carving it out. It carries little bits of that rock with it as it goes. So I always find that one interesting because when you look at just a drop of water in that stream isn't doing a lot, but when you combine them all together, then they are very powerful, especially over a long period of time. All right, so that is my simple experiment for you today. So my challenge for you now is, where else do you see surface tension taking place when you look around you? I think if you look around, you'll be able to find some other examples of it. Some of them are pretty neat. What else do you notice about this? What else do you think thinking about surface tension can tell you about liquids? What about other things? And can you think of any other experiments that you would want to do to experiment with surface tension? All right, so thank you everyone so much for joining me today. My name is Zach. This has been Science Explosion at Hudson Public Library, and I hope to see you again next time. Bye.